Okay, so section 3.2 is kind of a long section. We've now talked about open sets and we want to talk about closed sets now. So, something I will point out is that I am making a choice to deviate a little bit from what Abbott does in this section. He uses limit points to define closed sets, and I want to give you a different equivalent definition that I think is a little bit more intuitive. So here's my motivating question. Can you think of another mathematical context in which you have heard the term closed before? What should come to mind is something like the integers are closed under addition. Sets in general are closed under operation. So, example, a set is closed under an operation. My claim is that closed sets are just sets that are closed under a specific type of operation. So here, I'm going to give you the definition and then I will show you what I mean. So a set A that's a subset of R is closed, provided that for every sequence x sub n, that's a subset of values coming from A. So that just means xn's a sequence the way we're used to, but the values are elements of A. If xn converges to x, then x is also a value in A. So what we're saying here is that given a sequence of values from the set A, if that sequence converges, then its limit also has to be a member of A. So the limit of every convergent sequence of points from A must also be in A. And in this way, you can think of closed sets as being closed under sequence convergence because they must contain their limit. So let me write that out. So the limit of every convergent sequence of points from A must also be in A. Something to note here is that we're saying the limit of every convergent sequence. It is possible to come up with sequences from a closed set that diverge, but we only care about the convergent ones, and we want to make sure that when you have a convergent sequence, its limit stays in the set. So in this way, closed sets are closed under sequence convergence. So if we wanted to think about why a set is closed or why a set is not closed, sometimes it's easier to understand this property if we can take a look at when it fails. So let's take a look at this example. Y is A equal to the open interval 0, 1, not closed. And you could naively say, well, because it doesn't contain its endpoints. But what is it about not containing its endpoints that keeps this interval from being a closed set? So the first thing that you should do now is go up to the definition of closed and see if you can write a negation of it. So tell me what it means to not be closed. So A not closed would mean that there exists an xn, some sequence, that's a subset of points in A, such that xn converges to x, where x is not an element in A. So in other words, we're able to find a convergent sequence whose limit is not an A. In that way, we're not closed under sequence convergence. So I would like to do that for my specific example. So I need to come up with a sequence of points that's contained in the open interval 0, 1 that converges, but to a value outside of my set. And the key here is to think about our naive understanding of why this isn't closed. It's because it doesn't contain our endpoints. That gives us an idea about how we should construct sequences. Maybe we should make a sequence that converges to one of the endpoints. So construct a sequence xn that's in the open interval 0, 1 that converges to one of the endpoints. So, for example, I could let xn be the sequence 1 over n plus 1. We know that our standard prototypical sequence that converges to 0 is the sequence 1 over n, but notice that when n is 1, I would get the number 1 in my sequence, and that's not a value in my set. So we had to make this adjustment. I just added 1 to the denominator to guarantee that the sequence I'm working with is actually entirely made up of values that are between 0 and 1. So the issue here is I found an xn that's coming from my set, but if I look at xn, it's converging to 0. And 0 is not an element of my set. So by definition, because I've come up with a convergent sequence that leaves the set, whose limit is outside the set, 0, 1 is not closed. I could have constructed a different sequence that converged to 1, for example. The idea here is that when you want to prove a set is not closed, identify first what the limit points are that are a problem. That, can you find points outside the set that could be limits of sequences inside the set? So let's summarize that. So when trying to prove that A is not closed, first identify an X that is not in A that you believe could be a limit of a sequence in A. So oftentimes, hint, you want to use an X on the boundary of your set. So in our previous example, 0 and 1 were endpoints, so they were right on the edge of our set. And so conceivably, I should be able to come up with sequences from inside the set that converge to those points. Okay, so here's a question. If A is not closed, must A be open? We now know what open and closed both mean. And we want to make sure that we understand the relationship between the two. Now, I claim that there is a relationship between closed and open. However, it is not in this way. If A is not closed, must A be open? A classic example to show that the answer to this is no would be to use a half-open interval. So if I looked at this interval, for example, if I wanted to argue why my set is not closed, what would I do? Well, I would look at 0. 0 keeps A from being closed. And then 1 has no epsilon neighborhood around it that stays inside my set. So just as a reminder, here's 0, here's 1, here's my set. Any epsilon neighborhood that I try to put around 1 is going to contain points that are not in my set. So 1 keeps A from being open. So here we have a set that is not closed, but also not open. So the big thing I want you to take away from this is if we say not closed, that is not the same thing as saying open. So if you want to prove a set is not closed, and you prove instead that that set is open, you have not established that your set is not closed. Okay. Let's try an example where we actually prove that a set is closed. Well, let's go with our understanding of closed sets already. Let's take a closed interval and prove that that has to be a closed set. So for all A and B and R, with A less than B, the interval AB like that is a closed set. So let's just draw a picture real quick. All right, here's my set. Oftentimes, if you want to prove that a set is closed, it can be easier to argue by contradiction. So, for example, I could assume I'm not closed and then try to figure out what goes wrong. We're going to look at that for this case. So, our approach is going to be assume not closed and reach a contradiction. So then what that means is I'm going to assume that there exists an xn contained in AB such that xn converges to x, where x is not a value in my set. So without loss of generality, let's assume that x is greater than b. So I'm going to put my x value up here on the map. So here is my x. Somehow I'm going to create a sequence of values that come from the closed interval AB that are going to converge toward this x value, because I've assumed that I've started with points over here, maybe here's x1, x2, and they're all trapped inside. So what we're saying here is that my sequence xn lives here. But then it's somehow going to converge to that value, x. And we have to ask ourselves, what's wrong with this picture? Well, looking at it, there's a giant gap between where my set ends and where the limit is. And from this picture, on the one hand, I'm supposed to, if I pick this epsilon neighborhood that I've selected, so we'll call this V epsilon of x. On the one hand, xn is supposed to be inside that epsilon neighborhood. Its tail is supposed to eventually enter that neighborhood and never leave. But on the other hand, that neighborhood contains no points in A. And if it contains no points in A, it can't contain any values from the sequence, since all the values from my sequence came from my set A as well. So the key here is choose an epsilon neighborhood of x such that B epsilon of x contains no values from the closed interval AB. Xn converging to x says the tail of xn has to be contained in this epsilon neighborhood. But no xn can be in V epsilon, since xn is a member of this closed interval AB. And by construction, the epsilon neighborhood doesn't contain any of those values. So that's our contradiction. I'm going to write this up formally as a proof. So assume toward a contradiction that the interval AB is not closed. Then there has to exist some sequence contained in AB such that that sequence converges to an x value where x is not in that interval AB. Now, it could be that x is less than A or that x is less than B. Without loss of generality, though, we assume x is bigger than B, and that's why it's not in the interval. We said the key here is to choose an epsilon neighborhood of x that contains no values from AB, so it misses the set entirely. The way we can do that, going up to our picture, is to just measure this distance between x and the endpoint. We know it has to be a positive distance because we've assumed that that x is greater than b. So we let epsilon equal x minus b, and note epsilon is greater than 0 since we assumed x was greater than b. Since xn converges to x, there exists a capital N in the natural numbers such that for all little n greater than or equal to capital N, xn has to be a member of this epsilon neighborhood. However, by construction, if you look at the intersection between v epsilon x and that closed interval AB, it's empty. So since xn is in AB, xn cannot be in the epsilon neighborhood of x. And that's a contradiction. Thus, AB is closed.